Welcome to lecture 11. In this lecture we introduce linear systems and talk about their solvability. A system of linear equations or a linear system with m equations in n unknowns is usually written in the form a11 x1 plus a12 x2 plus etc. a1n xn equal to b1, a21 x1 plus a22 x2 plus etc. a2n xn equal to b2, etc. am1 x1 plus am2 x2 plus etc. amn xn equal to bm. If you take the coefficients of xi and write it as a matrix, this equation can be represented as ax equal to b, where the rows of a are the coefficients appearing in the first equation, second equation and so on. X is the vector, the column vector x1 x2 up to xn, or you can think of it as column matrix, n by 1 matrix, and b denotes the m by 1 matrix or the m vector, m column vector b1 b2 up to bm. Given matrix A in fm cross n, that is an m by n matrix A, and a vector b in fm cross 1, the column matrix b, then the system ax equal to b has m number of equations in n number of unknowns. The system ax equal to b is said to be solvable, also said to have a solution, if there exists a vector u in fn. That means you can think of it as a column vector in fn cross 1 such that au is equal to b. That is, if you look at au, the columns of au are nothing but, if you take u to be, write the vector u as u1 u2 up to un, then the columns of au, this we saw some time back, that au is u1 times the first column of a, u2 times the second column of a, and so on. So therefore b is written as linear combination of columns of a. That is, the system ax equal to b is solvable if and only if b is a linear combination of columns of a. Now ax equal to b has a unique solution. We say that it has a unique solution if b is a linear combination of columns of a. That means it is indeed a solution, it has a solution, and it is unique in the sense that there is only one way to represent b as a linear combination of columns of a. So this is equivalent to saying that the columns of a are linearly independent. If there are, one can see it easily. Suppose there are two solutions u1 and u2, au1 is equal to au2, u1 and u2 are distinct, which means that a of u1 minus u2 is 0. That means you have a if you take the entries of the vector u1 u2 un u1 minus u2 as, let's say, alpha 1 up to alpha n, that means alpha 1 c1 plus etc alpha n cn is 0, where c1 c2 up to cn are the columns of A, which means the columns are linearly dependent. So one can see that this has a unique solution if and only if the columns of A are linearly independent and B is a linear combination of columns of A. The homogeneous system corresponding to the system Ax equal to B is the system Ax equal to 0. Now the homogeneous system always has a solution, namely the 0 vector x equal to 0. It has infinitely many solutions if and only if it has one non-zero solution. Why is it so? If you take u to be a solution, then alpha u is a solution for any scalar alpha. So therefore, if u is a non-zero solution, then alpha u is a different non-zero solution for any alpha. So therefore it has infinitely many solutions. Now to study linear system, we use augmented matrix. So what you do is take A and augment B. You add another vector at the end, add B as the n plus first column. That is, the first n columns are A and n plus first column is B. We will look at first we look at some of the results on linear systems. We do a couple of examples and then we will prove these probably in the next lecture, in lecture 12. So what are the basic properties? So start with a matrix M by n matrix A and a vector B in M cross 1. Then the following are true. Suppose A prime B prime is obtained from AB by applying finite sequence of elementary row operations. That means you start with the augmented matrix A, B, and then apply elementary row operations on the rows of A appended with B and obtain A prime B prime. Then each solution of Ax equal to B is a solution of A prime x equal to B prime, and vice versa. This is easy to see because any elementary row operation is like you take that applying similar operation on the system of linear equations. Anyway, we will prove this in the next lecture. Now Ax equal to B has a solution if and only if a rank of AB is equal to rank of A. That means the number of linearly independent rows or number of linearly independent columns of the augmented matrix should be same as number of linearly independent rows or number of linearly independent columns of A. So a linear system Ax equal to B is said to be consistent if the rank of the augmented matrix is same as the rank of A. So only for consistent systems we can find solutions. Suppose U is a particular solution of Ax equal to B. Then each solution of Ax equal to B is given by U plus Y, where Y is a solution of the homogeneous system Ax equal to 0. So given any particular solution, you can find another solution by adding a vector which is solution to the homogeneous system Ax equal to 0. If R is the rank of the augmented matrix, which is same as rank of A, we need this to say that the system Ax equal to B has a solution. Suppose this is the rank is R and it is strictly less than n. Then there are n minus r unknowns which can take arbitrary values, and other r unknowns can be determined from the values of this n minus r unknowns. We will see this when we solve some of the linear equations, and also in the proof we will see it. If m is strictly less than n, then the homogeneous system has infinitely many solutions. If the number of rows is strictly less than the number of columns, that is, there are more number of variables than the number of equations, then the system has infinitely many solutions. Ax equal to B has a unique solution if and only if rank of the augmented matrix is equal to rank of A, and that should be equal to n, where n is the number of variables. If m is equal to n, that means A is a square matrix, then Ax equal to B has a unique solution if and only if determinant of A is non-zero. And the last one, we call it Cramer's rule. If m is equal to n and determinant of A is non-zero, then the solution of Ax equal to B is given by xj equal to determinant of ajb divided by determinant of A. So let me recall the definition of ajb. So for any vector B and a matrix A, ajb denotes the matrix with jth column of A replaced by the vector B. So you replace the jth column, remove the jth column, replace it by B, and then compute the determinant. That determinant divided by determinant of A is the solution of Ax equal to B. We will take up the proof in the next lecture. Now let's look at a couple of examples. So first we are given a system of linear equations. Find whether the system is consistent. So how do we find whether the system is consistent? We have to write down the augmented matrix and compute the rank. How do we compute the rank? Reduce the matrix to a row reduced echelon form and then look at the number of linearly independent rows or number of linearly independent columns. So our task is to reduce this coefficient matrix, augmented matrix, to row reduced echelon form. Write down the matrix: 5 with rows, 5 2 minus 3 1, 1 3 2 minus 2, 3 8 minus 7 5, and augment the vector b 7 11 8 as the last column, the fifth column. And then apply the elementary row operations. The first set of operations: r1 goes to 1 by 5 r1, r2 goes to r2 minus r1, and r3 goes to r3 minus 3 r1. So in the second and third operations, r1 denotes the modified r1 in the sense that after dividing by 5. So after doing this operation, we get the next matrix, and then apply next set of row operations. And in this row operation, you can see that the first 4 entries of the last row becomes 0, and the last entry is non-zero. So the number of pivots in this augmented matrix is 3, while the number of pivots in the, if you look at the first 3 by 4, the 3 by 4 matrix, that has only 2 pivots, which means the rank of A is 2 and rank of A augmented with B is 3. Therefore the rank of A augmented B is strictly bigger than rank of A, and the system is inconsistent. Let's look at another example. This is our basic Gauss-Jordan elimination. So in this Gauss-Jordan elimination, what one does is bring the coefficient matrix to a row reduced echelon form. So take this example: 5x1 plus 2x2 minus 3x3 plus x4 equal to 7, x1 minus 3x2 plus 2x3 minus 2x4 equal to 11, 3x1 plus 8x2 minus 7x3 plus 5x4 equal to minus 15. Take the coefficient matrix and look at the augmented matrix, and then reduce it to its row reduced echelon form. So the row reduced echelon form is given by applying set of operations. We get last row 0. So in this case, the number of pivots in A as well as in A augmented with B, both are 2. So therefore this is a consistent system. Now we can solve the system of linear equations. We write the new equation. So now we have obtained this new matrix by applying several elementary row operations. Our theorem states that the solution to both these systems are same. So now let's solve this. The first equation corresponds to the row reduced echelon form is x1 minus 5 by 17 times x3 minus 1 by 17 times x4 equal to 43 by 17, x2 minus 13 by 17 x3 plus 11 by 17 x4 equal to minus 48 by 17. So now here we have two equations and four unknowns. The unknowns corresponding to the pivots are called basic variables, and the other unknowns are called free variables. So from here, how do we proceed? We assign free variables to arbitrary numbers and then express the basic variables in terms of the free variables, and that gives us, in fact, infinitely many solutions. So assign alpha 3 to x3, alpha 4 to x4, and then you can write x2 equal to minus 48 by 17 plus 13 by 17 alpha 3 minus 11 by 17 alpha 4. And you can write x1 as 43 by 17 minus plus 5 by 17 alpha 3 plus 1 by 17 alpha 4. This concludes the lecture. We will take up the theorem in the next lecture and prove it.